Hello everyone, this is Universum, the place where you learn about the entire universe, how it began, and how it will end. Today, what we are going to be talking about is Lagrangians, and how they can apply to quantum mechanics. Yes, I am finally going to be talking about this topic in a little bit more detail. So now, first, for those of you who are a little bit new to Lagrangians, and well, might be a little bit weirded out at this point, you might be wondering, what is a Lagrangian in general? A Lagrangian basically is just plugging in the potential energy and then getting the kinetic energy of it. I know it's quite simple, but that's just in classical physics. And as it turns out, as you go up in physics, you actually will start to see more and more complex equations. Like, for instance, Lagrangians, they'll pop up in Schrodinger's equation, they'll pop up in the simple harmonic oscillator, or basically just a waveform, which then is going to be ultimately what that explains is that it's going to be doing a boundary condition to a particle. Say, for instance, let's say if you were to have a particle in a box, and that particle in the box had its own wave function. The wave function is going to be defined by an oscillating waveform. This oscillating waveform can be described by a Fourier Transform. A Fourier Transform meaning how many ways you can add up or subtract, or ultimately just any way you can manipulate a waveform in any way possible. That is getting a little bit into calculus, of course. And that is going to be getting into trigonometric functions, and then what we can do is that then after that you can plug in integrals. Then, well, of course, finding curved regions are a little bit harder than finding straight regions, so you're going to use Green's theorem for that. In fact, there actually is an entire book about this. Well, maybe not an entire book about that one topic, but an overview of calculus. In fact, it's actually a good book. I highly recommend it. It is an intro to calculus right here. It's a little bit like a crash course. I just wanted to look that out right now because, well, that's a really good book. So, anyways, getting back to Lagrangians and how they can be applied. A Lagrangian in a quantum harmonic system, what it can do is that ultimately it can tell you when a particle is in its ground state, or if it is in its higher up state, its first excited states. So a particle that is in the first normalized state, as quantum physicists call it, well, that is going to be the first ground state, and that's going to be the slowest of all the harmonic oscillators. Harmonic meaning that it rotates. Well, not necessarily, but harmonic basically just meaning that it is a wave function momentum operator. So then, basically, another way how you can visualize Lagrangians is in structural dynamics. Yes, and there actually are a few things in structural dynamics that do also use Lagrangians. Say, for instance, the delta operator, which is also going to be used in quantum mechanics as the delta Dirac function. Or say, for instance, if you're using it in structural dynamics itself, like let's say, if you were using the Euler-Lagrange equations. Now, Euler-Lagrange equations are a little bit harder, but they are quite easy Well, quite easy for some, but harder for others. So an Euler-Lagrange equation is basically an equation that is defined by a differential function. It is used in calculus of variations. An example of this equation would be the derivative of f sub epsilon over the derivative of epsilon is going to be equal to the derivative of x over the derivative of epsilon multiplied by the partial differential of the function of epsilon over the differential of x. Now, if you're wondering why epsilon is being used here so much, it's because they're Grassmann. And Grassmann variables are used a lot in here, especially in the form of integrals. And when they are used in integrals, that is what is going to be called a Gaussian integral. So anyway, continuing on, ultimately it just provides a proof. So say, for instance, you would add on to this a dg, a g being some sort of operator throughout this equation. And then you see yet again another operator, epsilon, sub epsilon. Not to the power, sub. And then that would be divided by d, d being derivative. Remember, d is always a derivative, and then the partial differential is represented by a weird it's a fancy D. That's kind of interesting. And then what happens next? That'd be multiplied by the same partial differential of f sub epsilon, and then ultimately what it's just doing is that it's just doing a repetitive pattern. So then what's going to be happening is that then as you would add this on to another differentiable equation, so say for instance d of g prime sub epsilon, prime meaning an anti-commutative derivative of it, and then you divide that by the derivative of epsilon, and then you multiply that by the partial differential of f sub epsilon, and then you know where we go from here. Then you go to the prime basis vector. And then since we're done with that section, now we need to be wondering, what does this equal to? This is going to be equal to the derivative of g sub epsilon over the derivative of e. Well, not e, not like Euler's number, but something like epsilon again. And then we're going to be doing the partial differential of f sub e. Then it's going to be over the partial differential of g sub epsilon plus derivative of g prime sub epsilon over derivative of epsilon. Then that's going to be multiplied by the partial differential of f sub epsilon. Remember, epsilon is going to be a Grassmann variable, and when you plug that in, remember that is going to be. Remember, when you plug it into an integral, that always is going to be a Gaussian integral. Remember that. And then what happens is then you multiply it, so then you divide it by the partial differential of g prime sub epsilon, and then that's going to be equal to nu. Now, I know it's a little bit of a hard one to pronounce, but it's a Greek letter, which kind of looks like an N, but except the front part of it is a little longer than the other parts. So ultimately, this just is representing a function. This is going to be representing a function of x. Yes, usually when you represent a function of x, they usually is going to be equal to some sort of derivative value of some sort of equation. So the equation that's representing is everything that came before it. And then that's going to be multiplied by the partial differential of f sub epsilon over the partial differential of g sub epsilon plus, well, you already know what goes on from here. It's just the prime basis vector of it. So if you're wondering what that would look like, basically it's just going to be n prime. Well, of course, n prime x. And then that is going to be multiplied by the partial differential of f sub e. And that's going to be over the partial differential of g prime sub e. Ultimately, whenever you have a prime basis vector, all of the priming goes down. It always is in the numerator. Now, if you guys just wanted to do a simple overview of it, then I'll tell you what a simplified version of the equation is. Partial differential of L over the partial differential of f minus d of dt multiplied by the partial differential of L over partial differential of f prime equals 0. Now, for those of you who don't know what this means, basically it means that the partial differential, which basically means a certain change in the third dimension of a certain Lagrangian, over the change in a function, well, a fancy change in function, and that's going to be minus the differentiable function of that same thing, except it needs to be primed. You define its antiderivative of it. And then when we put that all together, that's going to be equal to 0. Of course, then if you have dual primes, it's going to be equal to 1, of course. Yeah, but usually when it equals to 0, usually that means you either are 1 correct, unless you're doing different things. And of course, now, there actually are different variables that can be added instead of f. Like, for instance, there can be theta dots, or they can be psi. Ultimately, just any sort of Grassmann function you need. That is what you can add to it. So now that we've got the Euler-Lagrange equations covered, now we can wonder, what are they used for? Like, what is the sole purpose of them? So an Euler-Lagrange equation usually will look like usually you'll see a weird wave function equation, but if you were to add its imaginary component, you were stretch it out among the 3D or the algorithm's Cartesian plane, what you could do is that then you could find out its change. Now, what you could do is that, so by taking our past knowledge, so we need to find the ground state, which is going to be marked at 0, 0. And then we need to find its second one, which is going to be at some sort of point. Now, because quantum mechanics is a bit weird sometimes, Well, what may happen is that we may have some uncertainty, and that is what the Heisenberg uncertainty principle is. Ultimately, Heisenberg uncertainty principle is basically change in position multiplied by the change in momentum is going to be equal to, well, the h bar. H bar is going to be a certain constant, and the constant is going to be Planck's constant, which is simply going to act as a boundary operator, and that's going to be over 2 pi. Ultimately, what this means is that, so, the more you know about the change in momentum, the less you will know about the change in its position. I know, it's quite easy. So ultimately, if you know one, you can know the other. So like, for instance, so that's one interesting thing. So that means that, so you have to have some weirdness happening. So back to the particles in box situation. So let's say we were at 2 particles. We were to mark one as x1, well, x sub 1, just to be a little more fancy, and then x sub 2. Now, these particles are moving at 2 different rates. Now, what would happen is that one particle is moving at 1 speed. It'd be moving at the ground state speed, bouncing back and forth in the box, while the other particle is moving at a much faster speed, which is the more excited state, the first excited states. The first excited state looks a little sinusoidal at first, and then the other one looks a little bit more Gaussian. And that's the reason why I need a Gaussian integral for this. Now, Gaussian integrals, they are actually very, very fun, and also, in fact, and the more I know about them, the easier they get. And if you plug in Grassmann variables into Gaussian integrals, they just get simple as heck. So ultimately, Gaussian integrals, they can be defined as, Gaussian integral basically can be defined as the identity operator is going to be equal to the integral of negative infinity to infinity, then that's going to be e to the negative x squared dx. Now, when you plug in a Grassmann variable to this, however, what happens is that the dx is, well, it's going to be d psi, d theta, d xi, I don't care. It's any of them. Any variable you want to plug in, that's what d will change into. That's what the derivative will change into. It won't change into x, it won't change into y, it won't change into z. It will change into the derivative of your Grassmann variable. And that basically is how you find the identity of it. Now, ultimately, Gaussian integrals, of course, as we all know, are equal to the square root of pi over a. Now, you're probably wondering why. I mean, where's a circle? Like, sure, in a Gaussian distribution, where on earth is a circle in a Gaussian distribution? Well, we have to look a little bit closer into it. So if you stretch it out among the imaginary Cartesian plane, what you may notice is that from above, you may actually see a slice. And that slice is going to be a circle. And then, well, of course, the circumference of it is going to be indefinite pi. And then over the value of a basically it's simply just going to mean the slope, the derivative of the height of the Gaussian distribution. Of course, there are many, many different ways to represent this. So, for instance, let's say if you're to make your integral a little bit more complex. So, like, for instance, the integral from 0 to infinity multiplied by x to the 4th and multiplied by e to the negative x squared dx. Well, that is going to be equal to some sort of constant of pi. And if you're wondering what the exact constant is, that constant is going to be equal to the cube root of pi over 8. Okay, so now since we have a little bit more knowledge about what a Gaussian integral is, now, well, we probably have been asking the question that we all have been waiting for. What are the wave functions combined together? What are the combined wave functions of the 2 particles in the same box? Well, guess what? Use the Fourier Transform. All you have to do is add them together, and then boom. I know, it's quite a simple answer, but if you guys want a little bit more of a complex answer, I'll tell you what it is. So basically, what happens is that, Now, as you add them up together, what happens is then their frequency will change. The frequency of the wave function, they'll add up together. So remember, it is finite. The integral is going to be finite. So what you're supposed to do is that you're supposed to measure the area under it. And since because the most grasping variables are going to be absolute values, well, they may not appear completely sinusoidal. So ultimately, what you do is that as you add up the first ground state with the second excited states, what you'll get is a third excited state, and a fourth, and a fifth, until you get to infinite ones. And then you may get some really strange results. Like, for instance, you may even get some values where you might have a sinusoidal value right here, and then just shoots down, and then gets another sinusoidal value. I know, it's literally infinite possibilities. It's actually just very fun to play around with. So a Lagrangian in this equation, how are they used? Well, because the potential energy is measured by the first ground state and then to the first excited states. Now, what will happen is that as you're measuring the first states, well, what you're trying to do is that you're trying to measure what is the particle's amplitude of its wave function, its state, its speed, its momentum, its charge, its whatever. That is what is defined by its wave function, or its boundary conditions, or any of that. That is the wave function that is the wave function that is defined by the particle's absolute value. These are some very, very interesting things to talk about, and I definitely do genuinely enjoy talking about them. But ultimately, the more important thing is their importance in quantum mechanics and the way how we can define particles with them, the way how we can define particle speeds. I mean, if we can do this, we can find out the true nature of reality of particles. But there's one small flaw in this theory: string theory. String theory is what sort of screws it up a little bit, since now, of course, we'd have brains. We'd have 4 brains, 5 brains, all up to 9 brains. Of course, I know. Different professors will say different things. Some professors say that there can be up to 23 brains. Other professors say they can be up to 13. It's not necessarily that much determined. It all just matters on what type of heretic you are. Now, of course, heretic basically just means there are about 6 heretics. Now, heretic is basically just a type of string theory. And this type of string theory, well, it just is basically just telling you how many dimensions a process can be. And then, of course, the 6th one of the most important ones, is 11-dimensional supergravity, where things get really, really complicated. And then in the end, we actually found out that, well, if you combine all the heretics together, including 11-dimensional supergravity, all I have to do, cook it for 30 seconds, and then boom, you get M theory. And no, you don't have to literally cook it for 30 seconds, but I was just trying to. Okay, never mind. My jokes suck. Okay, anyways. Well, in the end, Lagrangians, they can do many, many things. A Lagrangian can be represented by integral, they can be represented by differentiating them, they can be represented in so many different ways. So many ways different possible, so many ways. They first were just thought back in the early 1800s just to define a pendulum speed, a ball on a pendulum just going back and forth, that can be represented by a derivative. And then as we got throughout it, then we started learning that they can be defined by integrals. What you can do is that then we can measure the speed of it by measuring the integral of its speed as it changes throughout a value of time, such as dt. And nowadays, we finally are finding out that they can be represented by particles, point particles to be exact, moving throughout one dimension. And that's what these particles are. They're moving from one dimension and then they get curved into the second dimension through a linear transformation. And that's how they get transformed into a certain type of wave function momentum operator. I hope you guys really like this video, and I'll see you guys next time.